Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The intellectual landscape of theoretical physics in the early 1920s was a territory of profound ferment, a domain where the established certainties of classical mechanics and electromagnetism coexisted uneasily with the strange and compelling postulates of the old quantum theory. It is within this specific milieu that we locate a minor yet illuminating work by a mind on the cusp of greatness, Wolfgang Pauli's 1924 paper on the absorption of gas molecules in strong magnetic fields. This essay undertakes a deep exegetical evaluation of this particular work, proceeding section by section through its internal claims and logical architecture. The analysis will focus with surgical precision on the paper's own arguments, methodologies, and conclusions, assessing their cogency within the scientific context of their time. Our purpose is to understand the work on its own terms, as a demonstration of a particular mode of scientific reasoning and a testament to the analytical prowess of its young author, all while exploring the inherent limitations and subtle implications of his chosen problem. We seek to reconstruct the intellectual exercise Pauli set for himself, evaluating the soundness of his steps and the ultimate significance of his calculated result, providing a scholarly portrait of a specific thought process captured in a singular academic publication. Section 1. The problem's formulation and foundational physical assumptions. Pauli commences his investigation by delineating a very specific physical scenario, one that marries the concerns of physical chemistry with the burgeoning interest in magnetic phenomena. He posits a system comprising a surface in thermal equilibrium with a surrounding gas composed of paramagnetic molecules. The central claim introduced at the outset is that the application of a strong, uniform external magnetic field will alter the equilibrium state of adsorption on this surface. The paper's entire logical trajectory is built upon this foundational hypothesis. Our evaluation must begin with the physical reasoning underwriting this initial setup. The choice of paramagnetic molecules is pivotal. These are molecules possessing a permanent magnetic dipole moment, a property understood from both classical theory and early quantum ideas like space quantization, which had received spectacular confirmation from the Stern-Gerlach experiment 2 years prior. The genius of the problem's formulation lies in its apparent simplicity. Pauli isolates a single, controllable external parameter, the magnetic field, and proposes to calculate its influence on a well-known thermodynamic property, the surface concentration of adsorbed molecules. The underlying physical mechanism he implicitly proposes is one of orientation. In the absence of a field, the magnetic dipoles of the gas molecules are randomly oriented. The introduction of an external field, he argues, will create a preferred alignment, lowering the potential energy for molecules oriented with a field. This change in potential energy, however subtle, must, according to the principles of statistical mechanics, shift the thermodynamic equilibrium. The internal logic is, from the perspective of 1924 physics, impeccable. It represents a direct and novel application of Maxwellian electromagnetism and Boltzmannian statistical mechanics to the phenomenon of surface adsorption, a field hitherto dominated by considerations of chemical bonds and van der Waals forces. The crucial assumption, which he leaves unstated in these opening remarks, is that the adsorption process itself is sufficiently sensitive to this magnetically induced energy change to produce a measurable effect. The elegance of the problem's framing resides in its reduction of a complex surface interaction to a single, calculable energetic term, a classic move of a theoretical physicist seeking a tractable problem. Section 2. The classical derivation of the interaction, energy. Having established the conceptual framework, Pauli proceeds to the core physical calculation, the derivation of the potential energy of an adsorbed molecule in the magnetic field. This section of the paper is a model of classical analytical mechanics, demonstrating the clean, rigorous style for which he was already becoming known. He models the paramagnetic molecule as a simple magnetic dipole with a moment of a fixed magnitude, which we can call mu, in the presence of an external magnetic field of strength H. The potential energy of this dipole is given by the classical expression U equals the negative product of the magnitude of the magnetic moment, the magnitude of the magnetic field, and the cosine of the angle theta between the dipole's axis and the field direction. This formulation is standard and represents a direct application of electromagnetic theory. The critical step in Pauli's argument, however, involves how this magnetic energy term combines with the energy of adsorption. He makes a simplifying, yet powerful, assumption the potential energy of a molecule on the surface can be decomposed into two independent parts. The first is the adsorption potential proper, which we can call W, representing the forces binding the molecule to the surface. Pauli treats this term as being independent of the molecule's orientation. The second part is the magnetic potential energy described above. Thus, the total potential energy of an adsorbed molecule becomes the sum W minus the product of mu, H, and the cosine of theta. The evaluation of this claim hinges on the validity of this decomposition. In reality, the forces responsible for this adsorption, such as dispersion forces, can themselves have a subtle dependence on molecular orientation. By treating the adsorption potential W as a simple scalar quantity, Pauli is effectively averaging over or ignoring these finer-grained effects. This is a legitimate and necessary simplification for making the problem solvable. It allows him to isolate the influence of the external field as a pure, additive perturbation. From an analytical standpoint, this is a masterful choice. It transforms the problem into one of calculating the statistical consequences. The single orientation-dependent term he has introduced, the physical fidelity of this assumption, is a separate question, and a point of vulnerability in the model. A critic could argue that the magnetic field might also influence the surface itself, or that the binding energy W is intrinsically linked to the molecule's orientation relative to the surface atoms, a complexity the model bypasses. Yet, for a first-order theoretical exploration, the assumption of separability provides a clean path forward and is a hallmark of this genre of theoretical physics. Section 3. The application of Boltzmann statistics to the adsorbed layer. With the energy landscape of a single adsorbed molecule defined, Pauli's next move is to apply the apparatus of classical statistical mechanics to determine the collective behavior of the entire population of molecules on the surface. This section represents the statistical heart of his argument. He aims to calculate the average orientation of the adsorbed molecules and, from this, the resulting change in the system's overall energy. The foundational principle he employs is the Boltzmann distribution, which states the probability of a system being in a state with energy E is proportional to the exponential function of the negative of the energy divided by the product of the Boltzmann constant K and the absolute temperature T. Pauli applies this principle to the continuous distribution of possible orientations for the molecular dipoles. To find the average value of any orientation-dependent quantity, one must integrate that quantity, weighted by the Boltzmann probability factor, over all possible solid angles. The specific quantity of interest for Pauli is the average alignment, related to the average of the cosine of the angle theta. This calculation is analogous to Paul Langevin's 1905 theory of paramagnetism, which calculated the bulk magnetization of a gas for magnetic dipoles. Pauli is, in essence, adapting the Langevin formalism to a two-dimensional population of adsorbed molecules. The mathematical steps involve setting up the appropriate integral for the partition function and for the thermal average of the cosine of theta. The calculation yields the well-known Langevin function, which describes the degree of alignment as a function of the ratio of the magnetic energy mu times h to the thermal energy k times t. The internal cogency of this section is exceptionally high, given the assumption of a classical dipole and the applicability of Boltzmann statistics. The mathematical derivation is straightforward and correct. It demonstrates Pauli's fluency with the tools of statistical mechanics. A subtle point of evaluation here concerns the classical treatment itself. By 1924, space quantization was an established experimental fact, suggesting that atomic magnetic moments could only take discrete, quantized orientations relative to an external field. A fully quantum mechanical treatment would replace the integral over all angles with a sum over these allowed quantum states. Pauli's use of the classical integral is therefore an approximation. However, it is what regime he is considering. For typical magnetic fields and temperatures, the energy difference between quantum states is much smaller than the thermal energy K times T, meaning the discrete quantum levels effectively blur into a continuum. In this high temperature, low field limit, the quantum calculation converges to the classical Langevin result. Therefore, Pauli's choice of the classical continuous model is not a sign of ignorance but a pragmatic and physically justified simplification, appropriate for discerning the general character and magnitude of the effect. One might even detect a touch of intellectual playfulness in his application of the elegant, continuous mathematics of the classical tradition to a problem whose microscopic underpinnings were known to be quantum. Section 4. The final calculation of the change in surface coverage. The culmination of Pauli's analytical effort is the calculation of the main quantity of interest, the change in the number of adsorbed molecules per unit area due to the magnetic field. This section ties together the energetic and statistical components of the preceding arguments into a final, predictive formula. The logic proceeds as follows: the magnetic field, by preferentially aligning the molecules, lowers the average potential energy of the adsorbed layer. According to thermodynamic principles, a lower energy state is more favorable, and thus, at equilibrium, the concentration of molecules on the surface should increase to take advantage of this new, more stable configuration. To quantify this, Pauli relates the change in surface concentration to the change in the Gibbs free energy of the adsorbed layer. He performs an expansion of the Langevin function for the case where the magnetic energy is much smaller than the thermal energy, a condition that holds for all but the most extreme and experimentally inaccessible circumstances. This expansion shows that the average energy reduction per molecule is proportional to the square of the magnetic field strength h and inversely proportional to the temperature T. The final result for the relative change in surface concentration, the change in n divided by n, becomes proportional to the square of the product of the molecular magnetic moment μ and the magnetic field strength h, and inversely proportional to the square of the product of the Boltzmann constant K and the absolute temperature T. The evaluation of this final claim must focus on its physical implications. The formula itself is a direct and sound consequence of the preceding steps. Its structure is physically intuitive. A stronger field or a larger molecular moment should produce a bigger effect, while higher temperatures, which promote random thermal motion, should diminish it. The most devastating critique of the paper's practical relevance, however, comes from substituting plausible physical values into this final equation. For a typical paramagnetic molecule like oxygen, in a very strong magnetic field of several Tesla, and at room temperature, the predicted relative change in surface concentration is minuscule, on the order of 1 part in a billion or even less. The effect is quadratic in the field and inverse quadratic in the temperature, making it extraordinarily weak. Pauli, with his formidable calculational ability, would have been fully aware of this. The paper, therefore, presents a curious paradox. It is a work of immense logical and mathematical rigor that culminates in a prediction of an effect so small as to be entirely beyond the detection capabilities of the era. The central claim is theoretically sound but practically ethereal. This outcome forces a re-evaluation of the paper's purpose. It appears less as a proposal for a new experimental discovery and more as a pure demonstration of theoretical principle, an exercise in applying established physics to a novel context to see where the logic leads, regardless of the physical magnitude of the result. Section 5. The implicit discussion of experimental realization. While Pauli's paper does not contain a lengthy, dedicated section on experimental methods, his entire analysis is framed by the implicit question of observability. The choices he makes throughout the derivation reflect a mind conscious of the parameters that an experimentalist would control: the magnetic field strength H and the temperature T. The final formula, with its explicit dependence on these variables, serves as a direct guide for any hypothetical attempt at verification. An evaluation of this implicit discussion reveals Pauli's deep understanding of the physical levers an experimenter could pull. The derived formula immediately suggests the necessary conditions. To maximize the effect, one must use a gas with the largest possible molecular magnetic moment, apply the strongest available magnetic field, and conduct the experiment at the lowest possible temperature. The inverse square dependence on temperature is particularly telling. It indicates that cryogenic conditions are essential. Halving the temperature would quadruple the effect, making this the most powerful experimental variable. Pauli's analysis, therefore, while leading to a discouragingly small number under normal conditions, simultaneously provides a clear recipe for how one might, in principle, amplify the phenomenon to the edge of observability. This foresight is a testament to his training in the Sommerfeld School, where a close connection between theory and experiment, even for the most abstract calculations, was highly valued. The paper acknowledges, through its mathematical structure, the immense practical challenge. It implicitly concedes that the effect is a delicate perturbation on the much larger forces of adsorption. One could interpret this as a form of intellectual honesty. Pauli presents the result of his pristine calculation without embellishment or any attempt to exaggerate its importance. He lays the theoretical groundwork and, in doing so, also lays bare the Herculean task that would face anyone attempting to confirm it. The paper thus functions as a theoretical feasibility study, one whose conclusion is that, while theoretically sound, the phenomenon resides far from the realm of 1920s experimental practice. This conclusion, embedded within the physics of the final equation, is perhaps the paper's most salient practical. Section 6. The paper's significance as an artifact of a pre-revolutionary mindset. To evaluate Pauli's 1924 paper solely on the physical magnitude of its predicted effect would be to miss its deeper significance as a historical and intellectual artifact. The work is a perfect specimen of a particular style of theoretical physics, one that was about to be superseded by the quantum revolution Pauli himself would help lead. The paper's claim to significance resides in its very methodology, the systematic application of classical mechanics and statistics, the clean separation of variables, the expansion in a small parameter, and the derivation of a precise, analytical formula all epitomize the highest ideals of 19th century theoretical physics as refined by figures like Boltzmann, Lorentz, and Langevin. In this paper, Pauli demonstrates his complete mastery of this classical toolkit. He wields it with an elegance and confidence that reveals why his older contemporaries held him in such high regard. The work can be seen as a final, perfect articulation of the classical approach to a problem involving magnetism and statistics. It exists in a fascinating state of tension with the quantum realities of the time. Pauli, the same man who was wrestling with the profound paradox of the anomalous Zeeman effect and the need for a new quantum number, here sets aside those deep troubles to solve a tidy, classical problem. The paper's conceptual framework contains no hint of wave functions, non-commuting operators, or the exclusion principle that would bear his name a year later. It is a work that looks backward in its methods to look forward at a new, unsolved problem. Its internal claims are all valid within its self-imposed classical boundaries. The paper's true value, therefore, is pedagogical and historical. It illustrates with supreme clarity how a first-rate mind approached a problem using the established principles, just before those principles were to be fundamentally rewritten. It is a snapshot of intellectual discipline and a quiet display of analytical power, a finger exercise performed by a master pianist, demonstrating flawless technique on a simple piece before turning to the revolutionary sonatas that would define his conclusion in final evaluation, Wolfgang Pauli's 1924 paper on the adsorption of gas molecules in strong magnetic fields stands as a work of impeccable internal logic and profound, if subtle, scholarly importance. Our section Bayesian analysis confirms that, within the classical framework it deliberately adopts, its claims are coherent, its mathematics rigorous, and its physical reasoning sound. The initial postulation of a magnetically influenced adsorption equilibrium is a novel and creative extension of established principles. The subsequent derivations of the orientation-dependent energy and the statistical mechanical consequences are executed with a characteristic clarity and precision. The work's primary predictive claim, an explicit formula for the change in surface concentration, is a correct and logical culmination of the preceding assumptions. The ultimate assessment, however, hinges on the magnitude and meaning of this result. The analysis reveals the predicted effect to be so vanishingly small under accessible conditions that the paper's direct contribution to experimental physics, or surface science, was negligible. Its claims, while theoretically valid, described a phenomenon existing more vibrantly in the equations than in the laboratory. The enduring significance of the paper, therefore, resides in what it reveals about its author and its era. It is a pristine example of the analytical style of the Sommerfeld school, a testament to the young Pauli's command of classical theory, and a valuable document of the intellectual toolkit of a physicist standing at the threshold of the quantum mechanical revolution. The paper is an exercise in theoretical purity, a demonstration that the consequences of physical principles could be pursued with relentless logic, even if they led to a whisper instead of a shout. It remains a fascinating portrait of a great mind in motion, a minor work that illuminates the methods, standards, and mindset animating one of the 20th century's most formidable scientific intellects.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.